Now we discuss electrochemistry. So, electrical energy plays an important role in many chemical reactions, and the study of production of electricity from energy released during spontaneous chemical reactions and the use of electrical energy to bring about non-spontaneous chemical transformation is called electrochemistry. The basis of these types of processes are redox reactions. So, what is electrolytic conduction? The power of electrolytes to conduct electric current is termed as conductance or conductivity. Like metallic conductors, electrolytic solutions also obey Ohm's law. What is Ohm's law? This law states that the current flowing through a conductor is directly proportional to the potential difference across it. So, if I is current and the potential difference is V, then I is directly proportional to V, or V equals to I times R. R is the proportionality constant, it is called resistance. Where I is the current strength as I mentioned, and V is the potential difference, and R is the resistance of the conductor. Some basic terms commonly used like resistance. So, it measures the obstruction to the flow of current. The resistance of any conductor is directly proportional to the length and inversely proportional to the area of the cross sections A. So, that R is, as I mentioned, R is proportional to length L here, and it is inversely proportional to the area of cross section A. So, R is proportional to L and R is inversely proportional to A. So, R is proportional to 1 by A. So, combining these two, we get R is proportional to L by A. So, if we remove the proportional sign here, so we need proportionality constant. So, R becomes rho times L by A, and its unit is called ohm. So, rho is called the specific resistance or resistivity. Now, what is resistivity or specific resistance? Resistivity is defined as the resistance of a conductor of 1 centimeter length having area of cross section equal to 1 centimeter raised to the 2. So, when L is 1 means 1 centimeter and A is 1 centimeter raised to the 2 means 1 centimeter square. So, the resistance is called the resistivity. Okay, so therefore, R is rho times L by A. So, if we just take the rho this side and take L and A other side, we get R is rho is R times A by L, and its unit is ohm centimeter, because R unit of R is ohm and unit of A is centimeter raised to the 2. So, you get unit of rho is ohm centimeter. So, R is ohm, unit of R is ohm, and unit of A, area of cross section, is centimeters raised to the 2, and unit of length is centimeter. So, if we use these three units here, so we get the unit of rho is ohm centimeter. Next, we discuss conductance. So, what is conductance? It is a measure of the ease with which the current flows through a conductor and is expressed as G. It is reciprocal of the resistance. So, higher the resistance, lower will be conductance, and vice versa. So, G equals to 1 by R, and its unit is ohm inverse, right. So, unit of R is ohm, and this symbol is ohm. Okay, omega symbol is ohm. So, unit of G is ohm inverse. Next, we discuss conductivity like resistivity. So, conductivity is the conductance of 1 centimeter cube of a solution of an electrolyte, and it is the inverse of resistivity. It is denoted by kappa K. Here it is kappa K. So, kappa is 1 by rho. Okay, that rho we already discussed. So, its unit will be, so unit of rho is ohm centimeter in ohm centimeter. So, unit of kappa is ohm inverse centimeter inverse. So, then next we discuss molar conductivity or molar conductance. Molar conductivity is defined as the conducting power of all ions produced by dissolving 1 mole of an electrolyte solution. It is denoted by lambda m stands for molar, so lambda usually used for conductivity and is related to specific conductance as lambda m. So is kappa by C, where C is the molar concentration. If C is in the units of molarity, then lambda m may be expressed as K, or sorry, kappa times 1000 by C. Next we discuss equivalent conductivity. It is defined as the conducting power of all the ions produced by dissolving 1 gram equivalent of an electrolyte in solution. So this is denoted as lambda C. So lambda C is capital lambda this one is. So lambda C is kappa times 1000 by C equivalent, and unit is ohm inverse centimeter square equivalent raised to the -1 per equivalent. So how do we calculate conductivity? So next we discuss calculation of conductivity. We have seen that conductivity kappa is reciprocal of resistivity rho. So kappa is 1 by rho here, and rho we already know, rho is R times A by L. So if we substitute the value of rho here in this expression, so we get 1 by R, okay, 1 by R L times A, L by A. Okay, so we get basically here 1 by R L by A. So now 1 by R is nothing but G, that we already discussed. So kappa is G times L by A. So here L by A is called cell constant. That is conductivity equals to conductance, G is the conductance, times cell constant. So this is very important things to remember. So conductivity is nothing but conductance times cell constant. Then we discuss Kohler's law. It says at infinite dilution, each ion contributes independently to the total molar conductivity of the electrolyte, and this contribution is characteristic constant for that ion. For example, if lambda naught K plus and lambda naught Cl minus are the limiting ionic molar conductivities of the limiting molar conductivity of KCl is given by, then the limiting molar conductivity, so this spelling is wrong. So yes. So the limiting molar conductivity of KCl is given by lambda naught KCl is lambda naught K plus plus lambda naught Cl minus. In general, if an electrolyte on dissociation gives nu plus cation and nu minus anion, then its limiting molar conductivity is given as nu naught lambda naught is nu plus times lambda naught plus nu minus times lambda naught. Okay. So here KCl dissociates or ionizes as K plus plus Cl minus. So nu plus is 1 for KCl and nu minus is also 1 for Cl minus. Okay. So for K the nu plus is 1, for Cl minus nu minus is 1 here. But for MgCl2 you get nu plus will be 1, but for Cl minus it will be 2, and so on. Next we discuss electrochemical cells or galvanic cells. The device in which chemical energy of a spontaneous redox reaction is converted into electrical energy are called electrochemical cells or galvanic cell. Okay, so in galvanic cell, chemical energy of a spontaneous redox reaction is converted into electrical energy. Okay. So in a galvanic cell you have this anode and you have one cathode here. Okay. In anode oxidation takes place. Okay. So anode means oxidation is taking place here. So anions, so if we have zinc sulfate solution, so you have zinc plus ion, it goes there, you have zinc electrode here and you have copper electrode here, and here zinc ions is moving from this cation goes to cathode and anion goes to anode. Okay, so zinc plus ion will go this side and sulfate ions will go this side. So we have the salt bridge here. So for the redox reaction, zinc plus copper gives zinc 2 plus and copper. So this is the redox reaction taking place here. The arrangement consists of two beakers, one of which contains 1 molar solution of zinc sulphate and another is 1 molar solution of CuSO4. So, here you have the zinc sulphate solution and here you have the copper sulphate solution. A zinc rod is dipped into zinc sulphate solution and while a copper rod is dipped into copper sulphate solution. Okay, so, here zinc rod is dipped into zinc sulphate solution and copper rod is dipped into copper sulphate solution. An ammeter is used to know the passage of current and the two openings of the U-turn tube is used to connect the two glass beakers and is called Sol bridge. So, this is the glass turn tube. So, this is called the Sol bridge here, and this is the ammeter is there to know the passage of current. Okay, when the circuit is completed by inserting the key on the circuit, the following observations are made. Zinc rod gradually loses its weight. So, we have zinc sulphate here and we have the zinc rod here. So, zinc rod will gradually lose its weight. Why? Because sulphate ion comes here and it takes zinc from there and we get zinc sulphate in this solution. Okay. So, zinc will gradually, the weight of zinc will gradually reduce here. The concentration of Zn plus 2 in ZnSO4 solution increases. Yeah, as I mentioned, so sulphate ion, because anion moves to anode and cations move to cathode. So, we have SO4 minus, so sulphate ions will come in this beaker and it will take zinc from this electrode. So, we get zinc sulphate in this solution. The volume of the solution of zinc sulphate will increase here in the anode. Okay, the copper gets deposited on the electrode. Okay, so here you have the copper sulphate solution. So, zinc ion will come in this beaker because this is cathode here. So, cation zinc will come in the cathode and we have the copper sulphate solution here, right. So, it will react with copper sulphate, zinc 2 plus will react with copper sulphate, we get zinc sulphate and copper. So, copper will be deposited here. So, that is why the copper gets deposited on the electrode. There is a flow of electrons in the external circuit from zinc rod to copper rod. Therefore, the current flows from copper to zinc, because current flows the opposite direction of the flow of electron. Now, what is Sol bridge and its functions? The Sol bridge is an inverted U-shaped tube filled with concentrated solution of inert electrolytes. Salts like KCl, KNO3, NH4NO3 are used. The saturated solutions of these electrolytes are prepared in agar-agar jelly or gelatin. So, important functions. So, Sol bridge completes the electrical circuit. Sol bridge maintains electrical neutrality of the two half cell solutions. Then we discuss EMF or cell potential. The potential difference between two electrodes of the cell, because we just discussed two electrodes, one is copper and another is zinc. So, the potential difference between two electrodes of the cell when either no or negligible current is allowed to flow in the circuit is known as EMF of a cell. It is expressed in volt. In the electrochemical cell, the reduction occurs at cathode. Okay, so, as I mentioned here, so zinc plus 2, zinc 2 plus goes to cathode here and then it loses 2 electron. Okay, and then you get zinc sulphate from zinc sulphate right here. Okay, so Zn2 plus will become Zn here. Okay, so reduction takes place in cathode and oxidation occurs at the anode. So, what we had here? So, we are getting, so sulphate is coming here, we had the zinc. So, zinc is oxidized to Zn2 plus here, whereas here copper is Cu2 plus is reduced to copper here, right. Okay, so in the cathode Cu2 plus is getting reduced to copper and in the anode Zn is oxidized to Zn2 plus. Therefore, EMF equals to reduction potential of the cathode minus reduction potential of anode. So, E cell will be E cathode minus E anode. So, standard electrode potential. Since a half cell is an electrochemical cell can work only in combination with other half shell does not work independently. It is not possible to determine the absolute electrode potential of an electrode. Okay, so half shell is not it cannot work independently. So we need other half. Okay, so we cannot calculate the absolute electrode potential of an electrode. To determine this difficulty, a reversible hydrogen electrode has been universally accepted as a reference electrode and is known as standard hydrogen electrode or SHE. So here it is the standard hydrogen electrode. So we have 1 molar HCl solution here, and then we have the platinum wire is dipped into it, and then hydrogen gas at 1 bar is inserted here, and then you get bubbles of escaping hydrogen, and we have a platinum foil coated with finely divided platinum here. So the following reactions occur in this half shell depending upon whether it acts as anode or cathode. If SHE or standard hydrogen electrode acts as anode, so as I said, in anode oxidation takes place, so hydrogen becomes H2 gas becomes H plus, so oxidation is taking place here. If SHE acts as cathode, so H plus is taking 2 electrons, gives H2. Okay, so in the reduction takes place in the cathode and oxidation takes place in the anode. This standard hydrogen electrode is also regarded as reversible electrode. So H2 is in equilibrium with 2H plus 2E minus. Next, we discuss electrochemical series. The arrangement of elements in order of increasing electrode potential values is called electrochemical series. So you can see as we go from bottom to top, okay, we can see the electrode potential value increases here, right? Okay. So as we move from bottom to top here, okay, so these are the stronger oxidizing agent, okay, and if we go from top to bottom, these will become stronger reducing agent, okay. So what I said here is, like if you consider your O2 and Cl2, so Cl2 is better oxidizing agent than O2. Similarly, if we consider Cl minus and F minus, so if Cl minus is the better stronger reducing agent than F minus, and these are the standard electrode potential values at 298 K. Then Nernst equation, the electrode potential depends upon the concentration of electrolyte solution. Nernst gave a relationship between electrode potentials and the concentration of electrolyte solution known as Nernst equation. For a general electrode reaction, Mn plus in aqueous solution plus Ne gives Ms, the Nernst equation is E Mn plus slash M is E naught, standard electrode potential E naught, Mn plus by M minus RT by Nf, Ln concentration of products by concentration of reactant. Or we can write, so this one is Ln, we can multiply 2.303, it becomes log here. So where E Mn plus slash M is known as electrode potential and E naught Mn plus by M known as standard electrode potential for 1 molar solution of metal ions. And R is gas constant and T is temperature, F is Faraday constant, and N is the number of electrons gained during the electrode reaction. So N is the number of electrons here in the redox reaction. Now if we substitute the values of R, so R 8.314 in joule unit if we substitute, and T is 298 K, and Faraday constant if we consider 96,500 coulomb, then the Nernst equation is E is E naught 0.059 by N log, this is log base 10 here, 1 by concentration of Mn plus in aqueous solution. Since concentration of solid phase Ms is taken to be unity. The Nernst equation can also be written as E equals to E naught 0.059 minus 0.059 by N log 1 by concentration of Mn plus aqueous at 25 degrees Celsius, because here actual equation is this one Actual equation is this one. So we are considering R is 8.314 and temperature you are putting 298 K. So this, and Faraday constant is 96,500. So this 0.059 this value we get when temperature is 298 K. Okay. We can also calculate equilibrium constant from Nernst equation. The EMF of the cell may be used to calculate the equilibrium constant for the cell reaction. At equilibrium, the electrode potentials of the two electrodes become equal so that EMF of the cell is 0. Consider the following redox reactions. So if we consider the reaction we considered before, actually we discussed. So Zn plus Cu2 plus gives Zn2 plus Cu. The reaction taking place in the oxidation half or in the anode. Okay, anode, what we get? So zinc goes to zinc becomes Zn2 plus. Okay, zinc oxidizes to Zn2 plus. And the reaction taking place in the reduction half, so copper 2 plus is getting reduced to copper. Okay. As the reaction progresses, there is decrease in concentration of Cu2 plus, just we discussed. When the EMF of the cells becomes 0, the reaction stops. The electrochemical cell is here to have attained equilibrium value. So when the cell when the EMF of the cell is 0, then the reaction does not take place anymore, and then we call that the electrochemical cell is said to have attained equilibrium value. Now let us assume that the concentration of Zn2 plus aqueous and Cu2 plus aqueous are equilibrium concentration and the equilibrium constant Kc. Then the equilibrium constant Ac, we can write that Kc is concentration of Zn2 plus by Cu2 plus. And the Nernst equation for the above reaction, we can write E cell is E naught cell minus 2.303 by RT times 2, number of electron is present here, or is number of electrons is 2 here. So this 2 value is coming here, and then F and log concentration of Zn2 plus by concentration of Cu2 plus. Now at equilibrium, as I said, E cell is 0 before we just discussed. So the above equation is E naught cell is 2.303 RT by 2F. So we get log times log Zn2 plus by Cu2 plus. So from there we can actually calculate the value of Kc. So this value is nothing but at equilibrium, this is nothing but Kc, okay, this quantity. So we get E naught cell is 2.303 RT by 2F times log Kc. So in general E naught cell is 2.303 RT by NF, because here 2 is coming because in number of electrons are involved here. So that's why the 2 is coming here. So in general it is the expression for it is the relationship between E naught cell and the equilibrium constant Kc. Okay, next we discuss electrochemical cell and Gibbs energy. In electrochemical cells, the chemical energy is converted into electrical energy. The cell potential is related to Gibbs energy change. We know that delta G reaction for a reaction is a measure of the maximum useful work that can be obtained from chemical reactions. For a reaction occurring in a electrochemical cell whose electrodes differ in a potential by E cell, the work done when amount of charge is NF is pushed along by the potential of the cell is given by NF E cell. So we get Wx is nothing but delta G naught reaction, we get minus NF E naught cell. Now relationship between the cell potential and Gibbs energy and equilibrium constant. Okay, so delta G naught we just got minus NF E naught. Okay, but E naught cell we already discussed. Okay, so E naught cell, value of E naught cell is 2.303 RT by NF times log Kc. So if we substitute the value of E naught here, okay, so we get delta G naught is minus NF times 2.303 RT by NF log Kc. So we get delta G naught is minus 2.303 RT log Kc. Or if we convert in natural or logarithm or log E base, we get minus RT ln K Kc here. Next we discuss relationship between EMF and ionic activity. Let A be the activity of ions in the cell, then the EMF of the cell can be written as E cell equals to E naught cell minus RT by NF ln A reactant, activity of reactants by activity of products. Now activity A we can write gamma times C, where gamma is the activity coefficient and C is the concentration. So this relation means that EMF is directly related to the logarithm of the activity of the ionic species involved in the electrode reaction. This can be explicitly written as this. Okay, so E cell equals to E naught cell minus RT by NF logarithm of activity oxidized by activity reduced. Then comes to concentration cell, a cell in which both the electrodes are the same type, but the solutions of electrolyte which they dip different concentrations is called concentration cell. For example, here you see we have two electrodes, same electrodes we are using, okay, same type, okay, here anode and cathode. And the solution we are using, this is less concentrated this side and the more concentrated this side, okay. And they are connected by salt bridge and the ammeter is there and so on. So electrons flow from less concentration to more concentration here. So this is known as concentration cell. So consider a copper ion concentration cell in which copper electrodes are dipped into two different concentrations C1 and C2. So Cu copper sulfate and the concentration of C1 and Cu sulfate C2 Cu, this is concentration of C2. So copper sulfate concentration, so in both cases in both electrodes we are using here copper, okay, anode and cathode both are using copper. The solution is also, electrolyte solution is also same copper sulfate, but the concentration of the copper sulfate is different in anode and cathode. One is C1 and another is C2. In this case, the cell potential is E cell is E naught cell minus RTF ln C1 by C2. Okay, so we just discussed here A oxidized by A reduced. Since E naught cell equals to 0 for concentration cell, so we have, because E naught cell because we have used the same electrodes, okay, in the both electrodes are the same here, so that's why E naught cell is 0. So we have E cell equals to minus RT by 2F ln C1 by C2, and if we consider this log value and if we put at 298 K, so at 225 degrees Celsius, we get E cell is 0.059 by N log C2 by C1. Now there are different types of concentration cell. First is electrode concentration cell. An electrode concentration cell is a type of electrochemical cell in which the EMF is generated due to the difference in concentration of the same ion across two identical electrodes immersed in the same electrolyte, but with electrodes themselves differing in concentration of a compound. So consider a typical hydrogen electrode concentration cell. So it's a platinum and then H2 at pressure P1, then H plus ion, again H plus ion, H2, pressure P2 and platinum, where P1 and P2 are the partial pressures of hydrogen gas at the left and right electrodes respectively. The half cell reactions can be written as, so anode oxidation takes place, so half H2 goes to H plus and plus 1 electron, and in cathode here we get H plus electron gives half H2 at pressure P2. So the overall cell reaction is half H2. So if we add them, we get half H2, pressure P1 is in equilibrium with half H2 at pressure P2. So the EMF of the cell can be written as E cell equals to E naught cell 0.059 by 1 log PH2 at pressure P2 raised to the half by PH2 partial pressure of H2 of pressure P1 raised to the half. As just discussed, so E naught cell is 0 because we get we have platinum here both cases, so we get 0 and 0.059 log P2 by P1 raised to the half, and then we get the value of E cell. E cell is 0.059 by 2 log P1 by P2. Then there is another type of concentration cell that is called electrolyte concentration cell. So within this one we get without transference. So concentration cell without transference are electrochemical cells where the two half cells containing solutions of different concentrations are connected but does not allow the transfer of ions directly between the solutions. So consider this cell, platinum, then hydrogen, and then HCl we have with concentration C1, and then HCl with concentration of C2 and H2, but the pressure is the same here for hydrogen and platinum. The half cell reaction, so anode in anode oxidation takes place, so H2 goes to H plus, so H2 becomes half H2 becomes H plus of concentration C1 and plus electron, and in cathode reduction takes place, so H plus at concentration C2 takes up 1 electron and gives half H2 at pressure P. So the overall cell reaction, if we add them, we get H plus at concentration C2 is in equilibrium with H plus at concentration C1. So we write EWOT. Okay, so we write we can see it. So this is without transference. So we write 0. So E naught cell is 0 here, and 1 electron is being involved here. So we write 0.0591 by 1 log C1 by C2. And if we carry out further, we get EWOT is 0.059 log C2 by C1. So for spontaneous reaction in the cell, so C2 has to be greater than C1. Okay, with transference. So in this type of concentration cell, both the different solution of the electrolyte are placed in the same container, separated by a membrane. If 1 Faraday of electricity is withdrawn from the cell reaction is written as like the platinum H2 at pressure P, and then HCl C1, HCl C2, H2P and PT. The overall cell reaction again here is half H2 gives H plus plus at concentration C1, and at cathode we get H plus concentration C2 plus takes up 1 electron, you get half H2. So at the anode, the hydrogen gas gets converted into H plus, which means that the hydrogen gas gets oxidized. Okay. At the cathode, the H plus combine to form H2, leaving behind the Cl minus ion, which means that the concentration of H plus in the anode is more than that in the cathode. And for Cl minus, the concentration is higher at the cathode. As a result, these ions will move in a direction in which their concentration is lower. Due to the difference in size of the ions, there will also be a difference in the speed of the ions. Okay, so speed of the ion depends on the size, or we can say this charge by size, charge by the radius ratio. The movement of cation and anion can be written as, so if we say that T plus times H plus goes to T plus H plus at concentration C2, this is concentration C1, and T minus times Cl minus times C2 goes to T minus Cl minus of concentration C1. So the overall cell reaction is this. So H2 plus H plus C2 plus T plus H plus C1 plus T minus Cl minus C2 produces H plus C1, and T1 times T plus times H plus at concentration C2, and T minus Cl minus of concentration C1. So if we rearrange the above equation, we actually end up with this equation: 1 minus T1 times H plus of concentration C2 plus T minus Cl minus of concentration C2 is in equilibrium with 1 minus T plus of concentration times H plus of concentration C1 plus T minus Cl minus of concentration C1. Since T plus and T minus equals to 1, so we can write T minus H plus of concentration C2 plus T minus Cl minus concentration C2 gives T minus H plus concentration C1 plus T minus Cl minus of concentration C1. So if we substitute, then we get the Tm EMF of the cell. So EMF Wt will be minus RT by 1F, then ILN. Then we substitute, we get C1 T minus C1 raised to the T minus, and times C1 raised to the T minus by C2 raised to the T minus, and C2 raised to the T minus. So if we carry out further, we arrive at this equation: EWT is 2T by 2T minus times RT by F ln C2 by C1.